Hello, in this lecture we will discuss something obvious, but probably important to remember. So methods are the elementary unit of reuse. Executing a method is reusing code, obviously. But when you define a method, it means that you enrich the API of the object, the application programming interface. And calling this method, this is the first level of reuse. So let's have a look at this case study. This is a long method, and this method is defined on a peer tree. That is a tree representing a document. This is part of the pillar package, okay? And we want to inspect this tree. It will return a presenter that displays this tree of node. And we have different kind of node inside this tree. We might have some paragraph, some titles, headers, whatever. And now we can wonder why clients of a document are forced to define this behavior here. Why should I test if the node that I want to display is a header? Why is it important that clients test this? In fact, it will be much better to separate things. And if I introduce correctly some display on strings, I define a new method on peer objects. This is the root of the hierarchy of all nodes. And I said that by default, when I want to transform a node to a string, it just displays its class name. And if I want to display as a string a header node, it means that I can reuse, I can extend the default behavior. It means that displaying its class name, but also I will concatenate the level of the title. So if you have trouble to understand this part, I invite you to revise the hooks and template lecture. This is a direct application of it. So now let's go back to our example. Now I can refactor my method. It's a little bit shorter, and I can use directly the newly defined display string on. And I can send it to all kinds of nodes, and it will correctly work. It means that the right method will be selected dynamically. Either it will be the default implementation that displays the class name, or if it is a header node, the level of the header will be correctly displayed also. So this is much simpler. And this is just because we enrich the API of nodes with the fact that they can display themselves as a string. So let's have a look at another example. This is a logic repetition. If I want to convert an object to a string, usually we are using this kind of pattern. I start by creating a string, and this string uses a string. I can send a printon method to the object and say, okay, display yourself on this string, and then I get the content of the string. So here, this is the kind of code that I should repeat over and over each time I want to convert any kind of object as a string. And the idea is, how can I avoid this kind of logic repetition? And in fact, this is implemented in the Faro library. And the method is named streamContains. And if you look at it, this method takes as an argument a block there. So this method encapsulates the string creation, so the string is correctly created. This method is optimized. We will see how later. It hides all the details, so it means that from the client point of view, I do not have to take care about creating the string, the stream, etc. And it encapsulates termination, as we will see. Let's have a look at this implementation. So in fact, this is not implemented in the string class. This is implemented in the sequentiable collection. And so this is implemented on class side, and it will be inherited by string class. So here, I can specify the default size of the string that will be created, and the important method is this one here. So first, we are creating the string, Okay? And now the important thing is that I got a block as argument, and I can execute this block here by passing the newly created stream. So it means that I can create the stream, I give it to the block, and the block is defined by the client. And then at the end, what is important there is a little optimization there. It means that if the string position is the same as the original content size, so it means that if I inserted 100 characters, for example, in the stream, I do not need to copy the contents, the buffer of the stream. I have exactly the buffer that has the right size, so I can directly send it. Okay, this is a little optimization. Another example of logic encapsulation is the following. We want to read from a file named Tintin, here using als file reference, and we are sending the message read stream do, and we pass a block to this method. And here in the implementation of this method, what it does is that it automatically creates the stream. Then the client block is executed by passing the stream that is just created before. And the really interesting point is that at the end of this method, it automatically ensures that the stream is closed. So it means that from the client point of view, we never deal with the fact that we need to close the file at the end of reading. So if we step back a little bit, in fact, what is really important is to avoid spreading knowledge in clients. It means that you need to encapsulate the logic inside the API. You need to prevent client to forget something, for example, closing a file. And one way to build this kind of powerful API is to use block closure. They are really useful to build this kind of abstraction over complex logic. But be careful, if you abuse about using blocks, it means that you will have really complex API, and I invite you to see the blocks-based object lecture.